In the previous video, we talked about the E2 reaction. The E2 reaction, in order to fully understand the E2 reaction in this video, what we're going to talk about is the stereochemistry of the E2 reaction and how that affects the structure of the products. Okay, so let's take this example. If we take this compound and treat it with sodium ethoxide to a small, strong base, the only product that's formed out of the reaction is this particular alkene. So the question that I'm posing here is that while two alkenes could theoretically form, both the E or Z one could theoretically form, only the E product is observed. Why is that? Okay, well, let's redraw this in a way that makes this question a little bit easier to answer. Let's abbreviate this as a phenyl group. So we'll have phenyl and the terbutyl group. And as if we rotate around this bond, that would orient the bromine up, and that would orient this methyl group up. So if we look at the beta positions, right, there's one hydrogen here, and there's no hydrogens here. So we have to form a double bond between these two carbons, right? If we form that double bond between those two carbons, you can imagine that there's two theoretically possible alkenes that could form. We could have a phenyl. So just to make this clear, we have a hydrogen here. We have a hydrogen here, and we're going to eliminate HBr, right? So on this side of the alkene, we're going to have a methyl and a phenyl. And on this side of the alkene, we're going to have a terbutyl and a hydrogen, right? But this bond can freely rotate, right? So we could just as easily have gotten, or at least theoretically speaking, had the terbutyl and the hydrogen in this arrangement. So notice the only product that we get is this particular product where the methyl and the terbutyl are on the same side and the hydrogen and the phenyl. This is the E product, right? The Z product is not observed. In order to understand why only this product is formed, we need to understand the mechanism on the level of the molecular orbitals. Let's take a very easy starting material and look at the orbitals that are involved in the E2 reaction. So if we just have chloroethane, and we use hydroxide as the base here. So the hydroxide is going to come in and form a bond to this hydrogen. These two electrons are going to be forming our pi bond, and these two electrons are going to be forming a lone pair of electrons on chlorine, right? So in the transition state, this bond is partially formed, this bond is partially broken, this bond is partially formed, and this bond is partially broken. And remember, in the SN2 reaction, right, this little lobe right here is the sigma star antibonding orbital, and this is where the nucleophile attacks. So electrons flow into this antibonding orbital, which starts to break this orbital. Well, in the E2 reaction, what we have is that these two electrons are flowing into that sigma star orbital. And so in order for those two orbitals to line up, right, what we need is this hydrogen to be anti to this chlorine, right? And remember, when we use the term anti, the easiest way to see that is with the Newman projection, right? So if we looked at this molecule, right, if we look down this bond, the hydrogen that's being eliminated, so we take this molecule and draw like this. The hydrogen and the chlorine are anti to one another. If we draw a Newman projection, right, in the back we have chlorine and hydrogen, and in the front we have hydrogen, hydrogen, hydrogen. But this one is the only one that can be eliminated, right, because it's the only one that's anti to the chlorine. It's the only one that can have electrons that are starting to flow into this antibonding orbital. So this bond has to be lined up with this antibonding orbital in order for this pi bond to start to form. And so these two things, the leaving group and the hydrogen that's being eliminated, must be anti to one another in order to undergo elimination. So like I said, let's look at this example once more. If we have the molecule that we were just talking about on the previous slide, so we have a phenyl and a tert-butyl, and the bromine is up and the methyl is up, and we look at a Newman projection here. Now what we're going to do is look down this bond. Then we have the hydrogen and the methyl and the phenyl, and notice that the hydrogen is anti to the bromine. So when we eliminate those two things, right, we get this alkene where the methyl and the tert-butyl are on the same side of the alkene and the hydrogen and the phenyl. But remember, what you want to be careful about is this carbon is bonded to a methyl and a phenyl, right? So this carbon is bonded to a methyl and a phenyl. And this carbon, which is the one behind, is bonded to a tert-butyl and a hydrogen. So make sure that you put the tert-butyl and the methyl together, but on different carbons, and you put the hydrogen and the phenyl together, but on different carbons. Okay, so let's look at all the different possibilities just to be perfectly clear here. So we have phenyl, tert-butyl, bromine, hydrogen, methyl, and hydrogen. I'm looking down this bond. So in the front, what I see is hydrogen, methyl, phenyl. And in the back, what I see is tert-butyl and hydrogen and bromine. Remember, this hydrogen is not being eliminated. It's this one, which is being eliminated. Luckily, it's already anti to the bromine, which is our leaving group. So when this undergoes elimination, we're going to get an alkene where these two groups are on the same side and these two groups are on the same side. But remember, they're bonded to different carbons. So the easiest way for me to do this is to just draw a carbon-carbon double bond, right? And on this carbon, we have a methyl and a phenyl. And then if we draw the other carbon, right, we have a tert-butyl, which is on the same side as the methyl, so we just draw it here. And we have a hydrogen, which is on the same side as the phenyl, so we draw it here. So notice that this is the lowest priority substituent, so this would be priority 2, this would be priority 2, so this is the E only. Okay. So what if we started with the other diastereomer, right? So let's imagine if this compound, so phenyl, tert-butyl, bromine is up, but methyl is back, and hydrogen is up. Remember, these are diastereomers. Let's imagine what product that we would get if this underwent elimination. I might have to erase this here. Okay. So we have bromine up, and we have hydrogen up, and we have methyl back. So now let's draw a Newman projection of this particular compound, right? In the front, we have methyl, hydrogen, phenyl, and in the back, we have bromine, hydrogen, and tert-butyl. So this is the only beta hydrogen. It's the only hydrogen on the carbon next door to the bromine. So this is the only hydrogen that can get eliminated, right? It's right here. This is the bromine that's going to undergo elimination, right? The problem is that they're not anti to one another. But remember, this bond can rotate, right? So what we need to do is rotate that so that the hydrogen becomes anti to the bromine. When we do that, we get a new Newman projection. So this hydrogen rotated over to where the methyl was, and the methyl rotated to where the phenyl was, and the phenyl rotated to where the hydrogen was, but we leave the back carbon untouched. But now, notice, we have an anti-configuration of the hydrogen and the bromine, so that these things get eliminated. Now these two things are on the same side, and these two things are on the same side. So when we draw our product, right, we have a carbon-carbon double bond, and on the first carbon we still have a phenyl and a methyl, but now on the same side of the phenyl is the tert-butyl, and now on the same side as the methyl is the hydrogen. So notice this is the lowest priority, this is the lowest priority, so now we got Z only. So you need to, when you only have one hydrogen that can eliminate, you must draw a Newman projection in order to figure out the correct product structure. Right. So what I illustrated in the previous slide was that these two compounds, right, so R1 and R2, R1 and R1 are cis here, R1 and R1 are trans here, so these are diastereomers. So if we start with different diastereomers of the substrate, we're actually going to get different diastereomers, the Z or the E diastereomer of the alkene. This is called stereoselectivity. So the E2 is a stereoselective reaction, meaning that this diastereomer will only give this diastereomeric product, and this diastereomer will only give this one. So you won't get mixtures, you'll only get this diastereomer or this diastereomer. Okay, so how do we predict which product that we're going to get in an E2 reaction? Well, it depends on how many hydrogens that you have at the beta position, right? So if you look at this molecule, notice that there's no hydrogens here, we can't eliminate this way. But we do have two hydrogens here. Elimination of one will give the trans product, elimination of the other will give the cis product. However, since we have a choice, the trans product is always going to be major over the cis. So if the beta position has two protons, expect cis and trans isomers with the trans being the major product. However, if you only have one beta hydrogen, right, now we must draw the Newman projection, and we must rotate this hydrogen over so that it's anti to the leaving group. Now notice that the diastereomer of the alkene that we're going to get is going to place a tert-butyl and the ethyl on the same side, and it's going to place the hydrogen and the methyl on the same side. So we're only going to get this isomer, which is, this is lowest priority, this is lowest priority, so only the E isomer is the only product that we get here. Okay, the last thing that I want to talk about is looking at chair conformations in order to understand elimination reactions. So it turns out that if this compound, let's say we treat it with sodium methoxide, it's a small base. We have two hydrogens here at the beta carbon, and we have two hydrogens here at the beta carbon. So our product, doesn't matter how we show this, is just going to be cyclohexane. But if we draw both chair conformations, what we'll find is that only one can undergo an E2 elimination, because now we know that you have to have an anti-arrangement of your leaving group and the hydrogen that's being removed. So this hydrogen is axial, this hydrogen is equatorial, and this hydrogen is axial, and this hydrogen is equatorial, and then we have. So these are our beta hydrogens here that I've drawn. Let's do the same thing here, hydrogen, 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 hydrogen. So if we're looking down, if we're remembering that this is the anti-bonding orbital for the chlorine, then this hydrogen CH bond here is lined up perfectly. So this is anti, this one can get eliminated. This one is not. This hydrogen cannot undergo elimination. This one can. This one cannot. So these two hydrogens can be removed by a base to form the alkene product. But notice, we're trying to find a pair of electrons that are anti to this bond. So notice that this is sticking up in this direction, this is sticking down in this direction, so they're anti to one another. We're trying to find the anti-bonds, the bonds that are anti to these chlorines, right? It's this carbon-carbon bond, and this carbon-carbon bond. So this conformation can't undergo E2 reaction. So this will not undergo E2 reaction because none of the hydrogens are anti to the leaving group. So it has to undergo a ring flip to go into a higher energy conformation in order to undergo elimination. Okay, so to summarize, we talked about two things, but we spent a lot of time talking about them. They're very important. The E2 reaction is stereospecific, and it must occur in an anti-coplanar conformation, which means just that the leaving group and the hydrogen are anti to one another, and they're in the same plane. So understand the implications for the E2 reaction of cyclohexanes, know how to draw the correct alkene isomer if an E2 reaction is taking place with a beta carbon that only has one hydrogen on it.